This year. Oh, you just got too much snow, right? Was there like a big snow? Or no, it's just
all right, so wow. Should have this in like an office or something. Yeah, exam three is three chapters. I posted a couple more old exams. One is called an exam 4. You should look at it. It's a summer class, so it was we did the schedule was different. And then if you didn't see my email, you should go back through a lot of the exams too that you looked at studying for our exam 2 had stuff that wasn't on there. A lot of email stuff got onto that. It got onto those exams. So 2 things are true. If you go back to those, work on those problems. If you somehow like accidentally work on an exam 2 problem, the cumulative final is a week after exam 3. So it's not like studying for exam 2 stuff at this point will hurt you. The other thing then is, so some preparing for the final, basically the final's cumulative. I would focus on the 3-hour exams we had in here, the 3 midterms we had in here, make sure you understand what you missed and have fixed it. And then the synthesis you're working on will draw from sort of the whole bit. Some of those problems require you to go back to basically day 1. So you should have in mind that you're going to be reviewing early material for that as well. Any questions before we start today? You'll get instructions. I've probably not made it terribly clear how exam 3 gets set up on Wednesday. So it's the Wednesday after we get back, and there'll be a lot of moving parts. All right. So some of you, probably most of you, will start it in here on time. It'll be 75 minutes. Some of you, if anybody has a bio exam immediately ahead of that, I'm going to start a group in the lab. If you get extra time and you're in my lab, you need to start down here because the lab exam is right after that. And we're going to do, I don't know if you're not in my lab section, if your instructor has talked to you about, like, you're going to have to come down here and do some task, like putting the lab back together at the end of the semester. Sort of every section has a different chore. My plan for my section is we're going to do the chore. Like, I think most professors are going to do the exam and then the chore. We're going to do the chore and then we'll do the exam at the end. So you guys, I know at least some people in here have 3 exams. Anybody in here who's in my lab has 2 exams. I'd like to give you a little bit of time between the 2. Love to know what you guys are whispering about. All right. Okay. No, I probably don't. I probably never want to know what you guys are whispering about. So today we're going to talk about polymers. And I've alluded to this. So we're going to give it like 1 lecture in here in class, which is not enough time. If you end up a chem major, there's a materials chemistry course, Chem 364, that covers some of this. You get a lot of this in some other classes, but polymers are an incredibly rich part of the chemical industry. Like, compared to how much we talk about it in the undergrad curriculum, you know, polymers are like 60% of the chemical industry, and we give it maybe a handful of lectures while you're in class. You might wonder why that is. The biggest reason, I think, is that if you're, especially in a chemistry department like ours, that we have a very new engineering department. We don't really have a chemical engineering department, so to speak. So there's not this sort of natural back and forth with engineers. And the other is, so if you think about what you've done so far in chemistry, everything's been molecular. right? So most of the faculty at Wake Forest think in terms of molecules. And with a molecule, or atoms, but atoms or molecules, you can measure how many of those molecules you have, and you could have it, in principle, you could have it be completely pure. Like you could have a sample of something that is 100% that molecule and nothing else. Polymers really don't work that way. All right, polymers are made up of molecules. The molecules are extremely large. The way we synthesize polymers, you don't end up with one molecule that you have lots of. You end up with lots of very big molecules. But so, let's put polystyrene together. So styrene, this. So polymers also get a lot of common names. You guys have heard of a bunch of these common names. You might have heard of Delrin, you've heard of PVC, you've heard of saran wrap. So I think I'm going to talk about saran here, but styrene, you've heard of polystyrene, right? You've heard that word. The way we name polymers, especially if there's just one monomer, it's just whatever the name of the monomer is, put a poly in front of it. Polyethylene, polystyrene. All right. So we're going to polymerize this thing, and if you look in the textbook, there are 3 types of polymerization. So we can have cationic polymerization, radical polymerization, and anionic. All right. Most molecules, most monomers polymerize better with one of those. Styrene can polymerize with all of them. So styrene can polymerize all these ways. So styrene here is going to be called, we're going to call this a monomer. The monomer is just the molecule or molecules that go into making a polymer, right? So if I'm a company making polystyrene, I have this big reactor and I charge it with styrene, maybe a solution of styrene. I add an initiator, I close the reactor up, I heat it up. At the end of it, I have polystyrene. All right, so I'm going to do a radical polymerization. I haven't talked about radicals much in here, and I'm not gonna ask any radical mechanisms on any of the exams. We haven't done radical mechanisms yet, but I'm going to draw through this, and then we'll talk about cationic and anionic. So you might remember, hopefully you remember, hopefully you saw some radical chemistry in Orgo 1. If you didn't, radicals don't, the reason I don't like to do mechanisms is they do not follow the rules that we have for Lewis acid base 2-electron chemistry. And right, even though you've had like a full year of organic chemistry, you're still trying to put that together, and I want you to have that down. Like 98% of the chemistry you'll ever see is going to be Lewis acid base 2-electron transfer chemistry. In radical processes, we have arrows can go together, right? These 2 arrows come together. These 2 arrows go apart. And the key thing here is I'm only putting 1 barb on the end of that arrow. This seems like a really weird, to me, this has always seemed like a weird linguistic trick. Each barb on the arrow, so when we do Lewis acids, right? Nucleophile, 2 electrons, we draw 2 barbs on the arrow. Those 2 electrons technically mean 2 electrons. Sorry, the 2 barbs mean 2 electrons. Like that's kind of weird, right? Because just you probably think arrows have 2, right? You put 2 barbs on the end of an arrow. Like if I just brought you in here and said draw an arrow, you'd put 2 barbs on the end. But the barbs actually mean electrons. So what's happening here is the pi bond, one of the 2 pi electrons is making a sigma bond with this single electron on the radical initiator. And one pi electron is going on the benzyl position to be a new radical. And so this, whatever this R dot is our initiator. And that could be a whole bunch of different kind of radicals. And then this reacts with another styrene. Right, so pH is just a benzene on the and the key thing here is each reaction leaves a radical. Right, so if we think about a polymer is just going to take a monomer and hook them together. So if we keep playing this out, a monomer reacts with another monomer, we get a dimer. The dimer reacts with a monomer, we get a trimer, so on and so forth. Your polymer then ends up, probably can't see that at home. Your polymer then ends up just a whole bunch of monomers hooked together. And so, like I said, the way we do this chemistry, we can't really control X. So then polymer science largely becomes statistical at that point. So you can sort of say this polymer I made, X is, the average X is 120,000 plus or minus 10,000, plus or minus 5,000, plus or minus 50,000. And so you would have, like if I made polystyrene with X is 120,000, changing the plus minus from 5,000 to 50,000 would change the properties of the polymer. So if you think about what we're doing with polymers, right? So we built this computer, whack the people at home, right? You want your computer to be hard, and you don't want it to get gooey if it gets hot. Right? But sometimes we do want it to be pliable, bendable. I don't want my computer to be able to bend because the motherboard can't bend, right? If the computer can bend, if the case can bend, I'm going to destroy my computer. But my water bottle, I don't want it to be stiff and cracked. I want it to give, so it will contain water. Right. So what polymer scientists end up doing is playing with the techniques. I'm drawing mechanisms here. You're going to play with time of reaction, concentrations, amount of initiator, temperature, all that sort of thing to try to control what comes out the other end. And then your polymer, like if we draw the polystyrene is going to end up looking like. We're going to terminate that at some point. We're going to have an X there, right? So polystyrene, we're just going to put a whole bunch of these styrenes together. And so this is an example of a chain growth polymerization. Right, so we start with a monomer, we have another monomer, and now that's our building chain. We keep adding monomers to that chain. I'll show you a step growth here in just a minute. You guys did both of these in the polymer lab, if you think back a few weeks. Questions so far?
So then, like, as it progresses, is it just like the doubling factor each time chains are together?
No, so that's the thing. In a chain growth, chains aren't coming together. Okay. Right. So styrene adds to styrene, we get a dimer of styrene. This then adds another styrene, not a dimer of styrene. It just adds a styrene. The step growth is what you're talking about. It doesn't have to be doubling, but in the step growth, well, you could imagine this termination step, right? This is, and the book goes into more detail on this. Right, that's your radical at the end of this. So the termination step, if you have some radical that can just add in there, right? We can make a bond like that. It could terminate. So we could grab that H, wind up with an alkene there. The other thing you could see is if you had another chain with a radical, they could add together. That's going to end up being, this is a weird thing about radical chemistry. The other reason I don't do radical chemistry as much as some of my colleagues is my PhD was in radical chemistry. It just hurts me to only talk about it. You know, so radicals adding together. Everybody thinks this radical, that radical, we make a bond. That's actually really rare because the concentration of radicals at any moment in solution is really low. And so it's unusual for two radicals to encounter one another. If they do, they can certainly make a bond. Yeah. Okay, so I'm going to just stick a T on here. There are so many termination steps, you guys. I'm not going to hold you responsible for knowing this. If you ever have to make like what the terminating group is though, like could matter. So if the terminating group here has, I don't know, carboxylate on it, it's going to be really different than if it has like a hydrocarbon thing. All right. So that makes polystyrene. I said styrene can do, so this would be the radical mechanism. We can also do, I'm going to take a shortcut. All right, we can do cationic growth as well, right? The initiator is not a radical, the initiator is a cation. That just changes all these to pluses, right? So the mechanism here is the pi electrons attack the R plus. That makes our carbon R bond and gives us the more stable cation. Another styrene can add in there and do that. That would give us this. And then at the end, we'd have a cation. And now the termination step's probably a little more obvious, right? If I have a carbocation, the termination step is going to be what? Water adds in to this thing, and at that point, that chain stops growing. Right, so I can change X by the concentration. If I have more styrene than water, I'm going to have more styrene than water. But if I lower the amount of water that's in there, we terminate less on. Right, so if you slow the termination step down, the chain grows bigger. If I accelerate the termination step, the chain grows smaller. In fact, right, you guys have done this reaction and stopped the chain at 1. So at some point in Orgo 1, I or somebody else told you to expose styrene to aqueous acid. So solvent is the water. And in that case, we just add OH onto the, right? We protonate with H plus. So the R is an H, and then water attacks the cation. We're done. So you actually have to watch out. And something, again, like this is something we probably don't educate enough on. If you guys go out in the world and are told to like do chemical reactions, there are a whole bunch of compounds that polymerize. Some compounds just polymerize if you look at it. And that's going to be the case anytime a molecule can react with itself. And so these styrenes, if I expose styrene to a little bit of an initiator, and again, it could be cationic, it could be radical, and it could be anionic, the styrene will just start polymerizing. So you might well, if you know, again, I'm assuming a lot of things. Let's say 5 years from now, your job is to do something with styrene in a biotech company. And you go pull the styrene off the shelf, right? You can keep styrene just in a brown bottle on the shelf. And you pull it down and you go to pour it out. Styrene should be a free-flowing liquid, but it's just this goop. What's happened is it's polymerized. It sat on the shelf too long and it polymerized. And you'll see this with a lot of organic compounds that they can polymerize. Yeah.
Can it not polymerize in water then?
It typically won't. You'll get water addition. Yeah. But you wouldn't, styrene's not miscible with water. All right, so some other things to look at here. Have what's called the repeat unit. So we tend to define a polymer by the repeat unit. If I ask you to write the structure of a polymer, right, like seriously, X could be 100,000. Right, asking you guys to just draw a molecule of polystyrene where X is 100,000 could occupy your junior year, right? We could just give you a big scroll in the library, like it's 13 the century, and you get just draw lines for this semester. So we tend to draw a structure with a repeat unit. And the repeat unit is just the smallest thing that you can find a pattern on. So for polystyrene, it's just going to be, right, the styrene without the pi bond. So the pi bond here used to be right there. So we're going to make a bond there and a bond there. And that will be our repeat unit. All right, so this is the case for a simple polymer where there's a single monomer. If you're ahead of the game, you might have noticed the phenols, the carbon with the phenols are all chiral centered. All right, so I don't know if people are still working on this or not. I know when I was in grad school, people were trying to come up with a way of making it where they would all be R or all be S. And best as I know, nobody ever figured this out real well. But you can do the alternating. And so we call this tacticity. And I'm going to let you look that up in the book, right? So if they're all the same direction, it's going to be called syneotactic. If it's random, it's called isotactic. There's a few different, right? Think about the patterns we might have. They might all be out pointed the same way. They might alternate. They could be random. And again, polymer science is not molecular science. So in molecular science, what we've done all semester, right? I draw molecules. I say that methyl and this carbonyl are trans. Every molecule in the sample, they're trans. Or maybe it's a 50-50 mix of diastereomers. But you never really have random. And so if I say this is syneotactic and X is 100,000, I guarantee you I do not have molecules where every one of those phenyl groups is the same direction. Most of them would be. How would you look at that? How would you study this? You could do optical rotation if it's not random, if it's enriched at all. The other thing we do, you guys will see this in biochem, is circular dichroism. So if you take a protein, right, all the amino acids in the protein are optically active. And so you get sort of a cumulative effect, and you can characterize proteins by, so what we do is we take a UV vis spectrum through polarizers, and we look at the curve, and you can actually characterize a protein really well with that. So speaking of that, I actually forgot at the very beginning, polymers aren't just human made. Right, so proteins are polymers of amino acids that have hooked together through amide bonds with side chains that vary with the amino acids. DNA is a polymer of 4 nucleotides. That's pretty cool. And again, DNA. So on the one hand, at one level, humans all have. You've heard of the Genome Project, right? You guys grew up with this, that we solved the human genome. Is there a human genome? There's not. You know how we know this? I mean, it's a simple answer. Like, look around the room. None of us look alike. Right? We're all different. And so that means the DNA in us is different. If you go molecule by molecule, if we just like, that's an A, that's a G, that's a C, we're just at some level. But that level's really far down, and we don't actually understand all the ways that affects us now, right? Like even our DNA, we took any one of our DNAs, compared it to a chimpanzee, it's not that different. And in fact, we share genes, and again, polymers with amoeba. I guess not viruses, but bacteria, single-celled organisms. So again, polymers are always going to be statistical. You're going to be able to characterize, if we characterized human DNA using polymer science techniques, basically comes out that it's the same. So what you have to do in the Genome Project is actually figure out every single position, which is pretty tricky. All right. So we've got chain growth method, cationic, radical. Like if this were anionic, you'd have an R minus here, it would add into the double bond, you'd have a minus, that would keep adding. I'll come back and show another example of that here. So let's get ready for a ride, guys. So let's do the one you guys did. Draw the polymer that comes out of this. Draw a repeat unit for that. This chemistry you've seen at least. So the important thing, even though I'm talking about polymer science, we characterize polymers using statistical methods. I'm going to come back to you could do NMR on these polymers. You don't get sharp peaks, right? So in this polystyrene, all these CH2s, they're all different, technically different, but they're really, really similar. So what you wind up with is just where you'd expect that peak to show up. It's just a giant clump, right? You don't see a triplet or a quintet or something. You see a whole bunch of overlapping peaks. So the chemistry works the same. If you're trying to figure out what the repeat unit here is, don't think about the whole reaction. Think about what an amine does with an acid chloride. So an amine with an acid chloride is going to make an amp. So you're going to get that. So this is where we get step growth. We're going to end up with, I'm not going to go through the whole mechanism. Maybe can't draw a 6-membered ring anymore. So the first is just a nitrogen adds in to an acid chloride. You make an amide, right? We make an amide bond. We still have an amine group. We still have an acid chloride group. These could swing around. You might want to swing this around. And I've talked about you guys need to be ready to make rings, right? Chemical reactions can make rings. This can break. In nature, not just in nature, you see a lot of 5- and 6-membered rings in nature because 5- and 6-membered rings form quickly. If you go back and think about chairs and envelope forms of cyclopentanes, the bonds are stable, they're clipped, they're staggered. Here, for this nitrogen to reach around here would be unlikely, right? It's a very long, big ring to form. It's depending on the concentration, it's a lot more likely to interact here. But for all these, all right, the important thing in a polymer monomer, you always need to have right? You need to have a monomer that's got 2 reactive sites on it, right? If a monomer only has 1 reactive site, it's just going to react to something and be done. So with an alkene, right, both carbons with the pi bond can react. When we put these together, we're in this OR box here, right? We've got a molecule with 2 amines and a molecule with 2 acid chlorides. Amine can react with an acid chloride. We still have 2 reactive sites. And so this would then add in another. You can see that it gets pretty cumbersome to draw the whole structure out. Right, so you make an amide on both of the acid chlorides, you still have two amines on the outside. And this is where now we could come in and we could put together two bigger molecules, right? So this might react with another one of these, right? The nitrogens don't have to just react with the diacid chloride. And in fact, after all of this molecule is consumed, we're still going to have oligomers that have two functional groups on them. We can still flip them. So now this nitrogen could attack here, could attack there. This nitrogen could attack another molecule of this. It could attack one of these, and so on, right? So the repeat unit ends up being, well, this, I'm going to go ahead and bring this out. I sometimes overestimate the repeat unit. Basically, here, right? That unit's going to repeat how many ever times? You guys remember what the, sorry.
So would this be like a lysotractive?
So we don't even really need the tactician, actually the stereochemistry here all comes from this. So, and this is not a optically active compound, it's just trans. The two nitrogens have to end up trans. Do you guys remember what we call a polymer that's made up of polyamides? This is, you guys made one of these. Wow. It's a polyamide. Got a common name. Wasn't the ink lab? You guys did. You did make that. Yeah, that was a polyaniline. So the other. Do you guys remember the polymer line?
Yeah.
Sorry. This is polyester. This is the polyamide. We didn't make slime.
So,
Nylon. Thank you. So this would be a nylon. Nylons are basically just polyamides. So if you take a diamine and a dicarboxylic acid or an acid chloride or an acid anhydride, you hook them together to make these polyamides. Those end up being called nylons. And again, like the nylon you guys made, it was the string that you pulled out of the solution. Like the whole point of these polymers, and we could, in principle, you could do this with molecules. It's just molecules tend not to behave this well enough, right? You can pull these polymers out and you can process them. So a lot of polymers, when you heat them up, they don't melt, but they do flow a little. We call it a glass transition temperature. And again, if you think about melting points, here's where I get punished for not doing melting points in my lab this semester. Yeah, all the other people, I shouldn't have said that. Nobody melts things anymore, all right? You take an NMR. Organic chemists look at NMRs and mass specs. We do not melt things. But think about what you know for melting points. We melt molecules, and there's a relatively sharp melting point. And the purer the molecule is, the sharper the melting, right? These are not pure. So even if it's pure molecules with this, X varies. Right? X is not going to be a single number. It's going to be an average. And so the wider that, again, there's going to be a standard deviation, right? So X is whatever, plus or minus whatever. The bigger that plus or minus is, the broader the glass transition temperature is. So this is going to be a solid to a liquid. And really, all it does is it changes the collection of molecules from something that's rigid to something that will float. So if I want to make water bottles, I just make a whole bunch of polyethylene, I heat it up, I pour it into a mold, then I cool it down. And so it's important to be able to have that. And again, this is step growth. Once you start adding these, the reaction is always an amine with an acid chloride to make an amide. But you could do this on a big chunk of molecules. You could bring two very large oligomers together to make a bigger polymer chain. You can have a polymer chain add one monomer, just like in the chain growth, but it doesn't have to only be the one monomer. Over here on the chain growth, I guess the way to say that is if you have two big pieces add together, they're going to do so in a way that they no longer add. That will have to be the end of the reaction. In step growth, if I take two big pieces that add together, they can still continue to grow. This also would be an example of a copolymer. So copolymers are going to have one or more monomers, two or more. So if we take this compound here, that's a CO. Draw the, you guys see that? Draw what you would get if you polymerize. So, anybody know the name of this? What is an alkene group if it's a substituent? The chloro is that. If that is a substituent, you guys might not know this name because we don't use it too much anymore in chemistry. But the name for this compound is called vinyl chloride. So an alkene group is a substituent. If you have just a 2-carbon, a CH2 group attached to something, that's a vinyl. I have no idea what the etymology is of that. Before telling you that, what would you guys, if I said vinyl, what would you have thought? What would you have thought of? Yeah, record. Why would you have thought of that? Why is that? Why is a record, why is that called vinyl? It's made of vinyl something. It's not this, but it's got vinyl groups in it. So if this is vinyl chloride, what is this? What is that? Anybody ever crawl around beneath your house? That is something you should all do. If you're going home at Thanksgiving, I expect you to crawl into your crawl space or basement. There's going to be big white pipes running, probably have blue lettering on it. Put your hand on that. Yeah. This is why you don't have to live in a place where there's a bunch of lead in your plumbing. It's just like monomer runoff. All right, so that's polyvinyl chloride. So seriously, you guys, if you haven't seen them, you should go. You can go to a hardware store if you don't want to see dirty ones. Actually, yeah, are there any in here? Probably not. These are all metal. This is a really old thing. And we try to keep the plumbing out of there. Like, it's one thing to have air flowing through your classrooms, but if we had like toilet runoff, that would be different. All right, so let's do. That's PVC. Maybe you guys know, I should have brought some PVC. I have some. All right, so draw the polymer you get out of this. All right, so again, you're going to add the initiator will add in. This initiator could be, for this one, could be cationic or radical. And then you'll have a radical here that could add there. You're always going to end up with a radical or the cation or the anion. Try to do all three as well. On the carbon with the chloride. But if you're wondering, well, would it be monochloro, then dichloro, then monochloro, then dichloro? It comes out to where it's pretty close to that. But it is going to end up being pretty random, right? You're not going to have real good control of that. So you can't really draw an easy repeat unit here. So that actually, you might think, like if you were to think chemically, how does this red polymer, copolymer look compared to PVC? You might think it should look really similar, right? If X is about the same, it should look pretty similar because you go from 1 chloride on a carbon to 2. But what happens is every polymer chain is molecularly a little different because it's fairly random. And probably X is different as well. I don't actually know like I don't make this stuff. But this is saran. So if you've heard of saran wrap? That's the polymer for that. So anytime you guys hear the word plastic in your head, you should hear the word polymer. Yep. Yeah, there's not really a unit. I think, I don't know, you're right, random decided. I take that back. I'm quite sure there's a way to do it. So yeah, we'll come back to the other end. I'll do some anionic chemistry. Point is, you can change fairly small changes in the monomer structure. And I guess the other thing I should say is, if you change the ratio of vinyl chloride to vinyl dichloride, right? I could have 9:1 vinyl chloride to 10 to 9 to vinyl chloride to 1 dichloride. I'm going to get a very different polymer than if I change that ratio to 1 to 9, right? I'm going to, like, how much of the two has a huge effect. And once again, I just want to emphasize, to successfully make a polymer, you've got to have monomers, either the same molecule or multiple molecules that have multiple different reactive sites. 2 amines, 2 chlorides, could be 3, could be 4. They can't be 1. right? If I come over here with my step growth and I just have like cyclohexylamine and I get rid of one of these acid chlorides, I make an amide and I have a molecule that doesn't have more reactive sites on it. And that's the problem. Gonna need to. So here's a good one. This is in the textbook. So maybe. Draw the polymer you get from that monomer and ask yourself. Yeah. So this monomer polymerizes and ask yourself, would the initiator be better to be a radical, a cation, or an anion? Right, so that's the polymer you get. The initiator is going to add into the unsubstituted into the alkene. That's going to give you a reactive site on the carbon between the two groups. It would be there. That will add into the unsubstituted end of another alkene. Reactive site there. On and on and on. Eventually you terminate by making some bond to that carbon. So what do you think? Radical, anion, or cation? So draw what you get if the initiator adds. You make an initiator alkene bond. This is going to go better as an anion, right? The ester, the carbonyl and the ester and the nitrile are electron withdrawing groups. So this is essentially enolate there, enolate onto the nitrile, partial positive carbon, partial positive carbon. If this was a plus, right, that would not be a very good cation. It could go, this could do a radical. Basically, all these alkenes can do radical initiation. And I would say it's probably like 40, 40, 20, maybe 45, 45, 10 radical cation and anionic initiation in the polymers that get made, right? And all the polymers that get made anywhere, maybe 50-50, it's radical and cation. And then there's a small percent in there, 10-15% that are anion. This one, you guys have probably done. You guys have all probably done this polymerization.
And it only happened through the alkene.
Yes, the alkene is the most reactive to it. And that's especially true in these alkenes, right? We talked about this last time. It's like a Michael addition, a 1,4 addition. That's especially true where the double bond is unsubstituted on one end. So this is, that alkene is electrophilic enough that water can add into it and initiate. So this substance, this monomer, you have to keep completely dry or it just polymerizes. And in fact, if you let it sit around in a tube for long enough, you go to open it and use it, it's probably polymerized. So it's got a short shelf life. That's super glue. Right, so you put when you super glue something, you're basically putting a pretty concentrated solution of this monomer on it. You put something else down on it, and there's enough water in there, like just draw a line on it. There's enough water from the air, enough water on whatever you're gluing to initiate the polymerization. And then this thing will wind up stuck. So one of the things you're gluing, it will have molecules of polymer, right? This is thing one you're trying to glue together, and that's thing two. And so you wind up with, zillions and zillions, for a technical term, molecules covalently attaching the two things you're trying to bond together. Skin does that really well too. Okay. You don't seem amazed by that at this point. All right, so draw that polymer. Draw the polymer you get out of this. And then name the monomer. So again, these alkene polymerizations, just going to be 2 carbons, whatever the least substituted carbon was bonded to. So naming this, what kind of compound is this? What are the functional groups that are present here? It's an ester and what else? Alkene and an ester. The alkene's going away. The ester's sticking around. So what is the name of this compound? What's the first word of this name? Methyl. You guys don't actually probably know the acid, right? So it's going to be methyl. The alcohol part of the ester is methyl. And then you would name at the end the carboxylic acid as an H. This is, what's that? No. It's a common name that you've also heard. It's methyl acrylate. You guys heard of acrylics? Acrylics are polymers, pretty common polymers that are around. A lot of these names of plastics that you've heard all your life are chemical names that get polymerized. So these are going to be, methyl acrylate is a pretty good, I think methacrylate. So if we put a methyl on there, right, you get a methyl here, and then this methyl methacrylate. The methacrylates, well, anyway, I think they're in glues. They're in some kind of glues. Seriously, the next time you're gluing something, pick up the ingredient list, look at it. You guys have had a year of organic chemistry, all right? If this does nothing else for you in your life, you should be able to pick up ingredients and know more what's in there than you did before. So if you look at glues, you're going to see things like methacrylate, acrylate. Right, that's also methacrylate, or sorry, that would be a methacrylate, but we're putting a triple bond in on the methyl. If you look at, like, have any of you ever stained wood or sealed wood, painted a wall? So those are polymers. The base for those are polymers. And they tend to be acrylates and methacrylates. And so what you would do, they're an amalgam, there's a ton of stuff in them. Right, so we might take a bunch of monomers like that. You guys don't have to draw that. All right, so you're going to get a bunch of monomers that have like a methyl ester. That ester is going to hydrogen bond, pretty short alkyl bit. That methyl makes it a little more hydrophobic. Put an octyl chain out here, put a butyl chain out here. Those become a little more hydrophobic. The carboxylic acid would, sorry, hydrophilic. No, hydrophobic. I had it written first. Let my instincts say I'm better at this. So if you put a bunch of alkyl groups on there, it becomes more hydrophobic. If you have a carboxylic acid, it's going to become more hydrophilic. So, right, if we decide to say we're going to put none of this in here, none of that, we're going to get a polymer base we call the latex, right, that isn't going to be soluble in water. So as you guys paint stuff, right, the choice is always, is it oil-based or is it water-based? The oil-based paints, which are, sturdier and are going to last longer, will, the reason they're in oil is that they don't dissolve in water. Right? So the latex I got out of these things would not be soluble in water. The carbon backbone is hydrophobic. The esters are all hydrophobic. As I add more and more acrylic acid in, or methacrylic acid in, it becomes more hydrophilic. And I can have a water-based latex. There are way more tricks than this done in the paint and coating industry. But like, people make loads of money. If you think about it, again, maybe you don't have the history yet. Painted walls today, if you use the high-end best paints today, they're way more durable than they used to be. Like, you used to have to paint your picket fence 3 times a season because the paint just wore off and couldn't take a scuff. People spend their entire careers trying to blend a more durable latex. You don't want it to be, you want it to be cheap. You want it to not like send toxic waste into the sewers. You want the 3-year-old to be able to, take a nail to it and scrape all over it. If you get dirt on it, you want to be able to just wash it off. You'd like to be able to go. That's the thing that blows my mind. When I was a kid, you could not just go up to a painted wall with like a little eraser and take stains off. You basically had to repaint it. You might have to strip it. Point is, this is what they're doing when they make more newer paints. Is they're changing the blend. Almost none of these, like I'm talking about copolymers, and the book talks about very regular things like block copolymers and alternating copolymers. Most of the polymers that are out there are sort of just, there's no molecular science to this at all, right? There's, let's change the ratio. You then approach it very methodically, right? We start with 25 of each, and then we start adjusting. And the way you test it, like how do I test? So we take an NMR of a molecule. How do I test what the paint is? Well, you make a paint, you put it on a board, and then you see if you can mark it. You see if you can erase it. They have a thing. So where my wife works, they have the test fence. It's an acre of just like these stands where you can set a 2x4 that you put paint or a coating on. You mark the date on it and they just go out and look at it. Seen boards that were painted 25 years ago. They bring them in for hurricanes. That's pretty cool. So anyway, the last thing I wanted to talk about is cross-linking. The great story is vulcanizing rubber, adding sulfur to rubber to create cross-links. They talk about that in the book. It's worth looking at. So if we just had two polyethylenes, right? So what holds these molecules together? Polyethylene, it's not one molecule. Your water bottle is not a single molecule, right? A bunch of different molecules. They're all incredibly large. So what's holding it together? Not hydrogen bonds. But you're on the right track. What else we got? We got hydrogen bonds, van der Waals, dipole dipole. Right? So polyethylene is literally just a hydrocarbon chain. So this is all going to be van der Waals. Van der Waals scales with size. So you guys might, this goes back to like day one. Well, I don't know who you had for Virgo and what day one was, but early in organic one, melting points, boiling points. Bigger the molecule, all else being equal, the bigger the molecules are, the higher the melting point and boiling point, because there's more van der Waals sticking them together. Right, so if hexane boils like 100 degrees higher than ethane, that's a pretty small change, right? If Y here is like 100,000, that molecule is going to be, is not going to boil for sure, and it's going to melt very high. So that's going to be polyethylenes held together just by van der Waals are going to be very malleable. But you can put in what's called a cross-link. Right? And now those molecules are going to be held together even harder. And so the more cross-links you have, in general, and again, this is, if they're not, we can't talk in, can't be specific because we're working with a statistical sample. So a cross-link is going to tend to increase the glass transition temperature and how rigid the polymer is. And rigidity is sometimes a good thing, right? Again, talking about the laptop there, I don't want my motherboard to bend, so I want my case to be not rigid. I don't want you to be able to just easily bend the thing. But what happens if I do try to bend that laptop? It cracks. So rigidity in a polymer also increases the chance that it's going to just crack. Right? If that was made of like water bottle plastic, well, I'd be able to bend my motherboard carrying it around. But at the same time, if I dropped it, it wouldn't crack. Obviously, the trade-off there is to be harder rather than more flexible. But depending on what you need, you can add cross-links to increase that. There's a couple of ways you might do that. Like if you think about how you might add a cross-link to polystyrene. Right, if I add, right, so most of this is styrene. It's going to polymerize the way styrene does. But I've got a few molecules in there that have 2 or 3 or 4 different alkenes on them. And so now this one right? If one of these gets caught up in the growing chain, it can just keep that chain growing, but it can also send out two branches elsewhere. I erased my example earlier, but the diamine I had, right? I could put a little bit of triamine in it. Makes sense? So that's all I have for polymers. So I say that's all I have for polymers. I'll take some questions, but I also, you could, you can do entire degrees in polymer science. I guess talking about characterization, that's really the thing. That's where polymer science differs from molecular science, is how we characterize them. So you can do CD, you can do circular dichroism or optical spectroscopy. You can do NMR, you can do IR. You can treat them exactly as if they're a molecule. But the other thing, and this is what more typically happens, most of the time, if you're trying to make a polymer, you have an end use in mind, right? So just like if I'm a medicinal chemist and I'm making a drug, sure, I can take all the NMR, get the mass spec, can melt it, run a TLC on it, get all that data. But what I really care about is, does it inhibit the enzyme I need to inhibit? Can I get it into cells? So that end use analysis is always going to be kind of the most critical. And for a polymer, what most of the time what they do is there are ways you can measure what X is, right? So you're basically X and Y here. And so if I have the blue line with X and blue line with Y, if X and Y are different, they have different molecular weights. They have different physical sizes, and I can separate them based on their physical size. So I can make a column that instead of being silica gel and I'm separating stuff based on hydrophobicity, I could have a gel that's got pockets that are a certain size. Anything bigger than that size can't go into the pockets, so it moves through faster. And then if I cross-link them, that's now a molecule that is much larger. Like that would, if X and Y are close to the same, that doubles the size of the molecule. So you can do all those. We can take NMR, we can measure an approximate molecular weight, we can get an idea of how polydispersed it is. So polydispersity is basically the error range. X equals whatever plus minus. That plus minus is the polydispersity. But what I'm probably going to do is take that very quickly and put it wherever I want it and test its use. I'm going to put it in a paint and I'm going to see if it sticks to the wall. I'm going to make a computer case and see if it will keep my motherboard from breaking in half. Are there questions on that? Okay, so I've got suggested problems up already. I will get this video up on that. Give me like 2 minutes. So I will take most of the questions on polymers from the book questions on the polymer chapter. Like I said, I added a few more old exams, but there's that big module that's got tons of old exams and stuff. I would dive into that looking for chapter 21, 22, and 27 questions. Class on Monday back here, so a week from today. God, it's only a week. Thanksgiving always seems like it occupies months of time. Anyway, a week from today, we'll meet in here. It will be a review session. I'll take questions. I may provide a few questions. And I'm trying to get a room booked for either that evening or Tuesday afternoon or something. So unfortunately, I've talked about like having an exam now and you don't get a lot of time to prepare, not wanting to have it the Monday after. So I don't want to have it the Monday after so you don't spend every waking moment of Thanksgiving break studying. I hate to tell you this because in an ideal world, you would have Thanksgiving break, completely free. Do some organic every day. Do a little bit, just like don't spend 4 hours doing organic when there's a turkey on the table. But look at it some. What else? Anything else to tell you? I guess that's it. So travel safe. I will, if you want to send me an email, I have meetings. I'm going straight from here to a meeting, so I can't hang around today. And then I'll be available a little bit tomorrow that we can arrange by email. If I don't see you, have a great break. And I'll see you back.
Like the paint research facility.
Yeah, she works for a company called Arkham.